Okay, so in this video I'm going to do the integral from 0 to infinity of sine x over x using the method of contour integration. Now, one of the usual ways of doing this integral is to use differentiation under the integral sign, but I'm going to show you my way of doing it using contour integration. Now, just a word of warning, if you haven't seen the video about this topic, I proved in an earlier video in this series that the sine of t is greater than or equal to 2t over pi for all values of t which belong to the closed interval from 0 to pi. And the proof of this used the mean value theorem. It's quite a straightforward proof, but if you haven't seen the video of this and you don't want to take this at face value, then by all means please go and look at it. It's quite a nice video, I think. And I'm going to use this inequality in order to do some of this integration here. So what I'm going to do first is I'm going to define my function f of z to be e to the iz over z. It's not quite sine z over z, but there's a good reason for that. So the exponential function is entire in the complex plane. It's holomorphic to every point in the complex plane. And in the denominator I've got a z, so that means I'm going to have a pole at the origin. So if I just go to my Argand diagram in the corner, I'll mark out where the pole is. So there's a simple pole which has multiplicity 1 at the origin. So what sort of contour am I going to use? Well, I'm going to use a semicircle with a smaller semicircle cut out from the middle. It's going to be what's called an indented, so let me write that down. It's an indented, don't really need the quotation marks, but here we go. An indented semicircular contour. And that basically means you've got a semicircle, but since there's a singularity or a pole at the origin, we're just going to jump over it just a little bit. So here's how the contour looks. It's traversed anti-clockwise and centered at the origin. I'm going to start at the real number epsilon, which is sufficiently close to 0, but not quite at 0. And that's going to go forwards along the real line to r, which is also greater than 0, and obviously greater than epsilon. And then I'm going to go around in an anti-clockwise sense, all the way to minus r, and I'm going to call this large arc gamma, big gamma. Then we're going to go back forwards towards the positive real axis again from minus r to minus epsilon, and then I'm going to traverse a smaller arc from minus epsilon to epsilon, and that arc is going to be called gamma. And that's how my contour is going to be traversed. One thing I should point out is that the arcs of these semicircular contours are traversed in opposite directions. So obviously this one goes this way and that one goes that way, and that's going to be important when we look at the integrals over those regions, over big gamma and little gamma. So how am I going to set up my integration using these paths? Well, let's see what we've got. Well, the integral over the whole contour C, so the integral over the whole contour C of f of z dz, that's equal to what? Well, I'm starting from epsilon and going to r, so I'd better integrate along that line segment first. So first I'm going to integrate from epsilon to r of f of z dz, and then when I've gone from epsilon to r, I'm then going to go whip all the way around along big gamma, so then I'm going to have to integrate over big gamma of f of z dz. Once I've done that, where am I at on the path? I'm now over here, which means I'm now going to have to integrate from minus r to minus epsilon. So I'm going to have to add on the integral from minus r to minus epsilon of f of z dz. And finally, I'm going to have to integrate over the little arc, which is this one here, and that takes me back to the start, back to epsilon. So I'm going to have to integrate over little gamma, little gamma f of z dz. Okay, so I've got 5 different integrals to deal with. What should I do first? Well, I'm going to look at the integral on the left first. Now, if you've looked at my previous videos in the contour integration series, normally what I do at this point is use the residue theorem, because normally there are some poles inside my contour, and I use the residue theorem and calculate the sum of the residues at each of the points, multiply that by 2 pi I, and then I can equate that equal to the right-hand side. But in this video, I'm not going to do that, because if you notice, the pole in question at the origin doesn't actually lie inside the contour, right? The contour just goes above it. So actually, by Cauchy's theorem, this whole integral is just equal to 0, because there are no poles inside the contour. Okay, so that takes care of 1 of 5 of the integrals. Next, I'm going to look at the first integral on the right-hand side and the third integral on the right-hand side. So these, this one and this one. And what I'm going to do is I'm going to try and see if I can make this third integral look like the first integral and try and combine them into one single integral so things are easier to deal with. So what's the integral from minus r to minus epsilon? So the integral from minus r to minus epsilon of f of z dz. So what does that look like? Well, using the definition of f, that's just the integral from minus r to minus epsilon of e to the iz over z dz, but this is being integrated over the real line. So what I'm going to do is I'm going to make the substitution z equals, let's say, minus x. And if z equals minus x, then obviously dz is minus dx, just taking that derivative of both sides. And how does that transform the integral? Well, if I apply that to my integral, then I get this. Well, what are my limits going to be? Well, when z is equal to minus r, then the only way that the right-hand side can be equal to minus r is if x equals r, so that's going to be r. And similarly, the only way the right-hand side can be equal to minus epsilon, so if z equals minus epsilon, x has got to be epsilon as well. Alright, so what happens to the integrand? Well, e to the iz is going to become, obviously, e to the minus ix, because I'm just replacing every instance of z with minus x. In the denominator, I'm going to have minus x as well, and dz is going to be minus dx, so I'm going to put a minus sign here, and dx over there. Now, one thing I can do immediately is cross out these negative signs, so these negative signs are going to cancel, and that's going to leave me with the integral from r to epsilon of e to the negative ix divided by x dx. Now also notice that I'm integrating from r to epsilon, but I want that to look like my integral from epsilon to r, because that if you look at my first integral, which is here, this one, it's from epsilon to r, which is the opposite order of the limits of integration of this one. So what I'm going to do is I'm going to multiply the whole integral by minus 1 and swap the limits. And if I do that, that won't change the value of the integral. So if I do that, I get that this integral is exactly the same as minus the integral, not from r to epsilon, but from epsilon to r, of e to the minus ix divided by x dx. Okay, I'm going to stop there. So how does that compare to this integral? Well, notice that if I did exactly the same thing with this integral, so if I wrote out f of z dz, I'd actually notice that this is true. I'd notice that the integral from epsilon to r of f of z dz, that would be exactly the same as the integral from epsilon to r of e to the ix divided by x dx. So now, if this is the first integral, and this is the third integral, and I add these two integrals together, so these two integrals are going to be added together, what does that give me? Well, I'm going to have, let's see if I can scroll down, that's going to give me the integral from epsilon to r of e to the ix over x dx, minus the integral from epsilon to r of e to the minus ix over x dx. And if I combine those two fractions together into one single integrand, that's going to give me the integral from epsilon to r of e to the ix minus e to the negative ix divided by x dx. And now this integrand might be looking a bit more familiar. So you might remember from the definition of the sine function that sine of x is equal to e to the ix minus e to the negative ix over 2i. So if I multiply both sides of the equation by 2i, I'm going to find that 2i sine x is just equal to e to the ix minus e to the negative ix. And obviously if I divide both sides by x, just like that, then I've got my integrand here on the right, so I can replace e to the ix minus e to the negative ix over x with 2i sine x over x. And so that tells me that that whole integral is equal to 2i times the integral of, well, from epsilon to r of sine x over x dx. Okay, so what I've done here is, let's see if I can scroll back up, I've combined the first integral and the third integral into one single integral. So this integral is now taken care of by Cauchy's theorem, this integral is taken care of, sort of, and this integral is taken care of. I'm going to leave those until I take the limit as epsilon goes to 0 and r goes to infinity. So now that just leaves me with two integrals left, the integrals over the curves. These are going to be the trickiest ones. I'm going to start with the integral over big gamma first. So what does that look like? Let's see here. So I want to look at the integral of big gamma of f of z dz. So what is that? That's the integral over gamma, and I'm going to want to have to use absolute value signs here, and that's going to be the integral, the absolute value of the integral of e to the iz divided by z dz, taken over the arc gamma. And I'm actually going to use a substitution here. So I'm going to let z be equal to r e to the it, and since my arc, if I show you on the diagram, goes from positive r to negative r, then I'm going to want t to vary from 0 to pi. And if I do that, r e to the it will just trace out this semicircle for me. And so, where's it gone? Here it is. So if z equals that, then obviously dz is the derivative of this thing, which is ir e to the it. So if I plug that, well, there's my dt as well. So if I plug that into my integral, I'm going to get the absolute value over gamma, well, not quite over gamma. It's going to go from 0 to pi, because t varies from 0 to pi. Let me just write this here. So 0 is less than or equal to t, which is less than or equal to pi, of e to the iz, but z is r e to the it. So let me just scroll up and make you see that. So e to the I z, which is ir e to the it, divided by z, which is r e to the it, times dz, which is ir e to the it dt. Now notice that I can immediately cancel a few things here. I can cancel this factor here with this factor, because r e to the it divided by r e to the it is just 1. And what I can also do here is I can bring out this I out in front, like this. So this is just equal to the absolute value of I times the integral from 0 to pi, integral from 0 to pi of e to the I r e to the it. I don't need this division sign, dt. And since I has modulus 1, I can just get rid of it. So this is exactly the same as the modulus of the integral from 0 to pi of e to the I r e to the it dt. And I'm going to do a trick now. I'm going to split this integral into two. I'm going to integrate from 0 to pi over 2 and from pi over 2 to pi. So this is the same as the sum, or the absolute value of the sum of the integrals from 0 to pi over 2, e to the I r e to the it dt, plus the integral from pi over 2 to pi of e to the I r e to the it. And I want to try and prove that these integrals are actually the same thing. So how am I going to do that? Well, let's look at the first integral first. So what's the first integral? See if I can scroll back down. Okay, so if I look at the integral from 0 to pi over 2 in absolute value signs of e to the I r e to the it dt, what is that? Well, e to the it is just the same as cos t plus I sine t, so that's equal to the integral, the absolute value of the integral from 0 to pi over 2 of e to the I r, replacing e to the it of cos t plus I sine t gives me cos t plus I sine t dt in absolute values. And that's the same as what? That's the same as the absolute value of the integral from 0 to pi over 2 of e to the I r cos t times e to the I squared r sine t dt. Now what I'm going to do is I'm going to use the triangle inequality for integrals, which basically says I'm allowed to bring the absolute value signs inside the integral. So that tells me that this is less than or equal to the integral from 0 to pi over 2 of modulus e to the I r cos t times modulus e to the I squared r sine t, which is just e to the minus r sine t because I squared is minus 1 dt. Okay, well I know that t is a real number, so therefore cos t is also a real number, and r is also a real number. So let's just draw this in. So this is actually a real number. And if this is a real number, then we know that e to the iy has modulus 1 for any values of y. So any real values of y, that is. If y were a complex number, this wouldn't quite be true. Okay, so if this whole thing is equal to 1, then I can get rid of it. So this is equal to 1. It traces out a unit circle in the complex plane. And I'm just left with this thing, modulus of e to the minus r sine t. Well, t is a real number, so sine t is also real. So r sine t is a real number, and I've got e to the power of a real number. Now, the exponential function over the real numbers is always a positive number. It's never negative, and it's never equal to 0. So this whole integral on the right of the inequality sign simplifies to the integral from 0 to pi over 2 of e to the minus r sine t. And I can drop the absolute value signs because the function is always positive. Okay, and what is that? Well, now I'm going to use the result I proved in a previous video, which says that sine t is greater than or equal to 2t over pi for all values of t in the interval from 0 to pi over 2. And by the way, this is the reason why I split the integral into two pieces. If this were an integral from 0 to pi, then I couldn't quite use this inequality, because this is only true, and it only holds on the interval from 0 to pi over 2, and that turns out to be exactly the integral, the region I'm integrating over right now. So that's why I can apply this inequality. So if I plug this in, remember if I multiply both sides by minus r, that becomes minus 2rt over pi, and this becomes a less than or equal to. So I can say that this is less than or equal to the integral from 0 to pi over 2 of what? E to the minus 2rt over pi dt. And this is something which I can integrate directly. That's the integral of what? That's going to be minus pi over 2r times e to the minus 2rt over pi, evaluated from 0 to pi over 2. And what does that give me? Well, I'm going to have minus pi over 2r times what? Well, if I plug in pi over 2 into here, I've got 2 over pi times pi over 2, so those both merge into 1, they cancel each other out. So I'm left with e to the minus r. So that the first term is going to be e to the minus r, and I've got a minus the value of this term evaluated at 0. I'm going to get e to the 0, which is just 1, so this is just minus 1. And if I expand this out, this is the same as pi divided by 2r, minus pi e to the minus r. And I want to take the limit, and this is being divided by 2r, and I want to take the limit as r goes to infinity. Now obviously if r goes to infinity, this term here, this term, that's going to go to 0 as r goes to infinity because the denominator is increasing but the numerator is staying constant, so this is definitely going to approach infinity at a faster rate. And what about this one? Well, in this case, e to the minus r, that goes to 0 as r goes to infinity because the exponential function e to the minus x decays for larger x. And 2r, that's also going to go to infinity as r goes to infinity. So in the denominator, I've got something going to infinity. In the numerator, I've got something going to 0. So this whole thing goes to 0 as r goes to infinity. And since both the terms themselves go to 0, then this whole thing has got to go to 0 as r goes to infinity. So if I scroll back up to where I split the integral up into two pieces, that's basically telling me that this integral here is going to go to 0 in the limit as r goes to infinity. And now I just need to do exactly the same process for this integral here. That's what I'll do next. So now I've got to work on the integral from pi over 2 to pi of e to the ir, e to the it dt, and that's in absolute value signs. Okay, and I want to try and show that this goes to 0. Well, I've just shown you that this is equal to the modulus from pi of the integral from pi over 2 to pi of e to the I r cos t e to the minus r sine t dt, and then I took the absolute value signs, the modulus signs inside the integral via the triangle inequality, and that gave me what? So this ended up being less than or equal to the integral from pi over 2 to pi. Remember, when I brought the absolute value signs inside, this term just went to 1 because e to the I y is, the absolute value of that is 1 for any real values of y. And I was just left with e to the minus r sine t dt. Now, unfortunately, I can't use my earlier result that sine t was greater than or equal to 2t over pi, so I'm not allowed to use that sort of bound just yet. So what I'm going to do instead is I'm going to massage or just see if I can change this integral to look like my earlier one. So I'm going to use a simple substitution. I'm going to let t be equal to pi minus u, or another way of writing that, if you put the u on that side and the t on this side, that's the same thing as saying that u is equal to pi minus t. And if I differentiate this, I get dt equals minus du. Okay, so how does that transform my integral? So that basically transforms my integral into this form. Well, when t is equal to pi over 2, then that must mean u must be equal to pi over 2 as well. So this is going to be an integral from pi over 2 to something. And when t is equal to pi, the only way that can be true is if u is equal to 0. So my limits of integration are pi over 2 and 0. And I'm going to have e to the minus r sine t, which is just e to the minus r sine of pi minus u. And dt is minus du, so I'm going to have a negative sign here and a du here. Now, just as I did before, I want to swap the limits of integration. I want this one to appear here, and I want 0 to appear at the lower limit. So I'm going to multiply the whole thing by minus 1 and swap the limits around. So that's going to give me the integral from 0 to pi over 2, because the negative signs are going to cancel when I do that, of e to the minus r sine pi minus u du. Now, using a trigonometric identity, we know that sine of pi minus u is the same as sine of u. So this whole integral here is just equal to the integral from 0 to pi over 2 of e to the minus r sine u du. But that integral we've just shown above, when, let's see if I've got it here. So I've just shown that you can integrate that by using this inequality to bound that by this exponential integral, which you can then integrate, and you can show after you've plugged in those limits that the whole term goes to 0. So we can immediately say, because we've just done all the hard work, that this goes to 0 as r goes to infinity. Okay, so what does that tell us? That tells us that this whole integral, where is it? Here. That tells us that this whole integral goes to 0 as r goes to infinity. So it has no net contribution. So that takes care of this integral. We've now only got one integral remaining. So we've got to deal with this integral over little gamma of f of z dz. So the integral over little gamma of f of z dz. So what's that? That's the same as the integral over little gamma of e to the I z divided by z dz. Okay, so what can I do now? Well, I'm going to use another little trick. I'm going to use the Taylor series of the exponential function. Well, recall that e to the x has the Taylor series expansion 1 plus x squared over 2 factorial plus x cubed over 3 factorial, and so on and so forth. And in any complex analysis course, you'll also prove that e to the iz also has a Taylor series just like this. It's 1 plus, if I just replace every x with iz, 1 plus iz squared over 2 factorial plus iz cubed over 3 factorial, and so on and so forth. And I want to see if I can use this in my integrand. Well, to do that, I'm going to have to divide both sides by z, and that's going to give me e to the iz over z is equal to 1 over z plus I squared z over 2 factorial plus I cubed z squared over 3 factorial, and just like that. And what I'm going to do next is the following. I'm not going to write this whole thing out when I go to integrate. I'm going to say that that's equal to 1 over z plus, let's say, e of z, capital E of z. And what is E of z exactly? Well, E of z is a power series, and that's a power series which is analytic on the entire complex plane. In fact, you can prove that the radius of convergence of that power series, if you've come across that before, is infinity. So it's holomorphic on the entire complex plane. And in particular, if it's holomorphic on the entire complex plane, it's continuous in any region of the complex plane. So if it's continuous in any region of the complex plane, it must achieve some upper bound over some interval. So in particular, over if we were to look at the maximum value of E of z, the modulus of E of z, where z varies along gamma, then that's going to be equal, it's going to achieve some upper bound m, where m is some positive number, right? And that's because it's continuous at any point on the complex plane. So how is that going to help me do my integral? Well, I'm just going to replace e to the iz over z with 1 over z plus this power series, which satisfies this. And that's going to give me what? That's going to give me the integral over gamma of 1 over z dz plus the integral over gamma of my power series e of z dz. And what I'm going to want to show is I want to show that this thing goes to 0, and I want to try and evaluate this thing directly. So let's do the second integral first. I know that the modulus of the integral over gamma of e of z dz, if I use the estimation lemma, or the ML inequality, that's less than or equal to the length of my curve gamma times the maximum of the modulus of e of z, where z varies along this path. Now, this is a semicircle which has radius epsilon, so I know that a circle has circumference 2 pi epsilon, so the semicircle has got to have length just pi epsilon, because it's half a circle. And this, I've just established, achieves some real number upper bound, m. So this whole thing is equal to pi epsilon m. But I'm interested in the limit as epsilon goes to 0. I'm going to try and shrink the indent to the origin. And so as epsilon goes to 0, this thing is obviously going to go to 0 as epsilon goes to 0. Okay, so that takes care of this contribution. Now what about this one? So what do I do about the integral of 1 over z dz over gamma? Well, this is a standard line integral. So what I'm going to do is I'm going to use a substitution. I'm going to let z be equal to epsilon e to the it. This is a parametrization of gamma. And t is going to vary from 0 to pi. So t is a real number from 0 to pi. And if I differentiate both sides of this equation, then I'm obviously going to get dz equals I epsilon e to the it dt. And how will that transform my integral? So this is going to be transformed as follows. Well, I'm going to have an integral, but notice that I'm not going to be integrating with the same limits as before. So if I look back to my contour all the way back over here, I'm now integrating from this point to this point. So I'm going in this direction. So I'm not going to integrate from t equals 0 to t equals pi. I'm going to integrate from t equals pi to t equals 0. Because I am actually integrating in the opposite direction compared to the bigger semicircle. So this is going to be the integral over the interval from pi to 0 of 1 over z, and z was epsilon e to the it, so this is going to be 1 over epsilon e to the it times I epsilon e to the it dt. And I can just cancel the factor of epsilon e to the it here, and the factor of epsilon e to the it here, and that's going to give me the integral of I I times the integral from 0 to pi of 1 dt, and this integral is just I times the integral of t from 0 to pi, and that's just going to be pi, or I times pi. Okay, so we've just established, where did I put it? So there's a step that I missed out here. I should have a negative sign here because I swapped the limits of integration. So this introduces a negative sign. So I'm going to have minus I times this. So this should be a negative I, and that should be negative I pi. So that means what? If I go back to my sum of integrals, that tells us that this integral is going to approach negative I pi as epsilon goes to 0. So putting it all together, what do we get? Well, this thing is equal to 0 by Cauchy's theorem. This integral plus this integral just goes to 2I times the integral from 0 to infinity of sine x over x. This integral goes to 0 as r goes to infinity, and this integral, as epsilon goes to 0, so as epsilon goes to 0, this goes to minus I pi. So putting it all together, we have, it's quite a lot of work here. So 0 is equal to 2I times the integral from 0 to infinity of sine x over x dx, plus a bunch of zeros, which cancel. And then I'm going to have minus I pi, and that was the integral over little gamma. That's where that contribution came from. And if I add I pi to both sides, I get I pi equals 2I times the integral from 0 to infinity of sine x over x dx. And if I divide both sides by 2I, like so, then that tells me that the integral from 0 to infinity of sine x over x dx, well, the i's are going to cancel, so that leaves me with pi over 2. So after all that hard work, we've managed to prove one of the most famous integrals is equal to pi over 2 using a method of contour integration. So that's all that I've got time for today. If you like this video, please leave a like, comment, and subscribe to the channel for more content just like this. Thanks.